Bismillahirrahmanirrahim. Welcome to Technogenier. I am Dr. Muhammad Yaqub. In this lecture, I will discuss the advanced features of microhydro power plant. In the previous lecture, we discussed about the basic concept of microhydro power plant, how we convert the potential energy of the water into electricity, and what are the basic formulas to convert the potential energy to electrical energy. So in this lecture, we will discuss specifically about turbines, impulse turbine, reaction turbine, and water wheel converters. So I will describe basic introduction of microhydro in the first few slides, and then I will go toward the turbines and their structures. So what is microhydro power plant? Microhydro power plant, as the name indicates, it is a microhydro. Micro means small hydro power plant. So specifically, a hydro power plant is basically a large scale power plant whose capacity is more than 30 megawatt. If the capacity of the power plant less than 30 megawatt, then it is called as micro hydro power plant. So it is also called as run of the river because we do not create any kind of reservoir like in big hydro power plant. We create a dam or a reservoir where we store the water and then control the water flow. But in a hydro power plant, we directly use the water flow through some channels and then produce electricity. So micro hydro power plant are basically small hydro power plant, and it is directly connected to the load. It does not require any transmission line infrastructure because the capacity to generate electricity is very low. So this is the basic structure of a hydro power plant. This is the main water line where the water is flowing. We took some of the water by developing the structure, concrete structure, which is known as channel, and diverting the water flow to a certain path where we develop a small tank which is known as 4-bay tank, and from that 4-bay tank we divert the water to a small pipe which is normal. The material of that pipe is specifically PVC pipe or a plastic pipe, and then we divert this water flow to a turbine, and based on this water flow the turbine start rotating and it will produce electricity. And if you see, this is basically the 4-bay tank, and from the 4-bay tank we divert the water through a pipe which is normally known as penstoke. The 4-bay tank height is normally high compared to the water level or the ground level. So that height is basically the potential energy of the water, and then we use penstoke to increase the pressure of the water by putting the water in some pipe, and that pressure is basically pressure energy, and then it comes from a nozzle, and that nozzle due to that nozzle, because the diameter of the nozzle is lesser than the diameter of the pipe, so water comes with certain pressure, and that pressure is called kinetic energy, and due to that pressure we rotate the turbine. So this is the complete structure of micro hydro power plant. We have 4-bay, which is at certain height, and then we use penstoke, and from the penstoke it diverted to the generator or the turbine. So the height of the 4-bay is basically the gross head or HG, but there is some loss, and that loss is head loss, which can be represented at delta H, and so the overall head or the difference is basically the difference between gross head and the head loss, that is called as net head, and from the net head we produce electricity. So we have two types of materials. One is materials of the pipes are basically of two types. One is basically PVC pipe, and the second type is polyethylene pipes. Polyethylene pipes are basically rubber type pipes that can be that can be transferred in the form of roll. But PVC pipes are basically rigid plastic pipes, and the transportation become very difficult. However, the efficiency of the PVC pipe is much greater than the efficiency of the poly pipe, because the friction loss in poly pipes are comparatively high as compared to the PVC pipe. So there are different kind of standards which are used in poly pipes and PVC pipe. The minimum size is basically 1.5 inch and the maximum size is 5-inch PVC pipe. And when the size increases, we prefer to use PVC pipe compared to the polyethylene pipes. So now the turbine. In the previous lecture, I discussed that there are three different types of energy which are produced. That is potential energy, pressure energy, and kinetic energy. So we have to convert these energies into electricity. So there are three different approaches to transforming the water power into mechanical power in order to rotate the turbine, and from that turbine we need to rotate the generator to produce electricity. So there are three types of turbines which are used. One is impulse turbine, second one is reaction turbine, and third one is water wheel converters. So what is the impulse turbine? Impulse turbines capture the kinetic energy of high speed jet of water onto the bucket along with the circumference of the wheel. In contrast, the water velocity in a reaction turbine play only a modest role, and instead it is mostly the pressure difference across the runner or the blade of the turbine that create the desired torque. Generally speaking, impulse turbine are most appropriate in high head, where the height of the head is very high. So for that purpose, impulse turbine produces a huge pressure, and that pressure is converted into mechanical energy. So if the low flow circumstances, while the opposite is in the case of reaction turbine. So if the flow is low or the height of the head is high, then we prefer to use impulse turbine. But if the height is low and the flow is high, then we prefer to use reaction turbine. And finally, if the slow moving but powerful traditional overshoot, then we use water wheel to convert potential energy into mechanical energy. So this is a basic figure of the impulse turbine. If you see, there are two nozzles which are with certain pressure. They push the turbine wheel, and the turbine will start rotating. While in the reaction turbine, we have a special kind of water, a special kind of structure of the turbine, where we use the pressure of the water, and that pressure of the water start rotating the turbine. So this is the mechanical structure of impulse turbine, and this is the mechanical structure of the reaction turbine. So if you see the water flow and it hit the paddles of the turbine, but in the reaction turbine it do not hit, and it just flow in a certain direction, and due to the water pressure it will start rotating. While the water wheels are different kind of structures. If you see, this is undershoot water wheel, where the water wheel is on the upside and the water is under the wheel, and due to the pressure or the flow of the water, this wheel start rotating. Similarly, this structure is basically called as stream wheel, where water is continuously flowing at down level, and water and due to the flow of the water, this will start rotating. And this is another type of the or undershoot uh, wheel water wheel. Now this is another type. This is basically breastshoot water wheel. Similarly, this is overshoot water wheel, where the water is above the turbine, and due to the flow of the water, the turbine start rotating. And this is backshoot water wheel, where the wheel rotating in opposite direction. Like in this breast shoot wheel, the wheel rotate in clockwise direction. In the back shoot, the wheel rotates in anti-clockwise direction. So impulse turbines are the most commonly used turbine in microhydro. The original impulse turbine was developed and patented by Lester Pelton in 1880, and its modern counterpart continue to carry his name. In a Pelton wheel, water squirted out of the nozzle onto set of twin buckets attached to the rotating wheel. The buckets are carefully designed to extract as much of the water kinetic energy as possible while leaving enough energy in the water to enable it to leave to the bucket without interfering with with the incoming water. So there is a diagram where we use four nozzles and the Pelton wheel, which will be shown in the next slide. These turbines has an efficiency of almost 70 to 90%. So this is basically an impulse turbine where we have four impulse and if you see these are the structure of these nozzles is basically this one. The nozzle have a have a small opening which is specifically called as jet opening, which will produce a certain pressure, and due to that pressure this turbine start rotating, and after certain time another impulse will help to continue the flow of the water. So this is the basic structure of the four nozzle Pelton turbine. The flow rate or to a Pelton wheel is controlled by a nozzle, which for simple residential systems are much like those found for ordinary irrigation sprinklers. When water exit a nozzle, its pressure head is converted to kinetic energy, which means that can be used to determine the flow velocity. So this is the head velocity, head Hn, which is basically the square of the velocity divided by 2g. So the velocity is equal to under root 2g Hn. So from the velocity v, flow rate q, we can determine an appropriate diameter of the water jet. For the nozzle with the needle valve, the jet diameter is on the order of 10 to 20% smaller than the nozzle size. But for simple home scale system, the jet and the nozzle diameter are nearly equal. Using Q is equal to VA along with 4.14 equation, which we discussed in previous slide. So we use the overall equation is Q. This is the flow rate is equal to velocity into area, and the velocity which we calculate in this equation, we put the value of the velocity, and the area is pi by 4 into n time d square, where n is the number of nozzles. So if we convert this formula and calculate the value of the d, then the overall formula will be d is equal to 0.949 divided by g into hn raised to power 1 by 4, and then square root of q divided by n. So this is the basic formula of the impulse turbine and specifically the diameter of the jet. So this is an example. A pen stroke provide 150 gallon per minute, that is approximately equal to 0.334 CFS with 50 feet of head to a Pelton turbine with 4 nozzle. Assuming jet and the nozzle diameter are same, pick a nozzle diameter. In this example we have to calculate the nozzle diameter, so we will use this equation 4.16. So this is the diameter is equal to 0.4949 divided by the values 32.2, which is the value of the g, and then we use h, and h is 50 feet, which is shown in this statement, and then we use the value of q, which is the flow rate, and that is 0.334 cfc divided by 4, and the overall result is 0.52 inch. That is basically the diameter of the nozzle. And there are some other types of impulse turbine that is known as turbo wheel. The efficiency of the original Pelton design suffers somewhat at higher flow rate because water trying to leave the bucket tend to interfere with the upcoming water. Another impulse turbine called turbo wheel is similar to the Pelton turbine, but the runner have a different shape, and the incoming jet of water hit the blade somewhat from one side, allowing the existing water to leave from the other side. If you see, this is the inlet and this is the turbo runner, this is the generator, and the water goes outside. When the inlet water hit the turbine, it start rotating and the remaining water go outside. So the turbo design also allows the jet to spray several buckets at once. This spin the turbine at higher speed than Pelton turbine, which makes it somewhat more compatible with the generator speed. So there is another type of the impulse turbine that is called cross flow turbine, which is specially used in low to medium head situations, where the head height is 5 to 20 meters. This turbine is also called as Benke Mitchell or Osberger turbine, name that reflects its inventor, principal developer, and the current manufacturer. These turbines are specially simple to fabricate, which makes them popular in developing countries where they can be built locally. So this is the water inlet, and due to this water inlet, this turbine start rotating, and this is the outlet where the water goes out, so it do not disturb the flow of the turbine. Now, the large MicroHydro system may be used as a source of AC power that is fed directly into the utility lines using conventional synchronous generator and grid interface. So, since the output frequency is determined by the RPM of the generator, very precise speed controllers are necessary. So, actually we need to develop 50 hertz of frequency. So, in order to develop 50 hertz, we control the RPM through some control circuit and maintain the speed which can produce 50 hertz. While mechanical governor and hand operator control the valve have been traditionally used, modern systems have electronic governors controlled by the microprocessor. So this is basically the turbine, and with the flow of the turbine, there are special controllers which controls the RPM and maintain the RPM according to the requirement in order to produce 50 or 60 hertz, which can be directly supplied to the end consumer. So on the other hand of the scale, home size microhydro systems usually generate DC, which is used to charge the batteries. The battery bank is standalone microhydro system, allow the hydro system including pipe, valves and turbine to be designed to meet just average daily power demand rather than the peak, which means that everything can be smaller and cheaper. So we produce electricity from the turbine, but we use special DC generators which can give output supply to the batteries, and batteries start charging. Load vary throughout the day, of course, as appliances are turned on or off, but real peaks in demands are associated with the surge of the current need to start motors in major appliances and power tools. So when we start the motor, the initial current of the motor is comparatively very high as compared to the continuous running current of the motor. So in order to maintain the power flow, or to accommodate the surge, we use battery that will handle the starting current of the motors. So this is the basic structure of micro hydro power plant. We have turbine. From the turbine, the generator will produce DC output, and from the DC output we have special charge controller which are designed to charge the batteries. and protect the batteries from overcharging or undercharging. So we have two phenomena for the batteries. One is SOC, that is state of charge, and second one is depth of discharge. So we have to protect the batteries from both the things. So we do not want our battery to charge to continuously charge and we do not want our batteries to discharge at the dead end. So we have to maintain the batteries for the charging and discharging in between 20% to 80%. So from when the battery is charged, we have DC to AC converter for the AC load, and we have simple DC load which are directly connected to the batteries, or that can be directly connected to the charge controller. So other control schemes are possible, including use of the regulator that are either adjust the flow of the water through the turbine or modulate the generator output by adjusting the current to its field winding. So batteries can be provided DC power directly to some load, while other load receive AC from an inverter. Thank you, Jazakallah. Hopefully, you understand the major concept of the micro hydro power plant and the turbines. And if you have any query or question, please write in the comment section. Stay blessed. Allah Hafiz.